like the Eurographics logo thing.
I see video unavailable. The video has been removed by the uploader.
Oh, I see Eurographic Euroviz with a
video has been removed by the uploader. Okay.
Oh,
I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Oh, I'm uploader is wrong, then I'll figure. Fifth try, got it. Yep. Great, thanks. And so I should be fielding questions from today. The first paper will be Asynchronous Eulerian Fluid Simulation, and the speaker will be Tatsuya Koike.
Okay, I'd like to thank you for giving me the chance to speak here today. I'm Tatsuya Koike from Waseda University. The presentation title is Asynchronous Eulerian Liquid Simulation. We researched about liquid simulation based on the Eulerian method. We propose a method that advances decomposed simulation domain with different time steps and reduces the total runtime of the simulation. Such method is called asynchronous time step method. Each decomposed domain is called as level. Time step for advanced then has n times interval. To perform our proposal method, We decompose the domain to ensure all the local CFL number falls in the target range. And we propose advection scheme that is absence of visible seams on boundaries of a region of different time step. And interpolate Eulerian materials such as level set, velocity, and pressure. And we also propose regional pressure solver supported by the boundary values interpolated from a region with different time step. In this presentation, we will mainly describe above three contributions. If you want to know the details, please read our paper. Overview of our method is illustrated in this figure. At first, we decompose the simulation domain into several clusters. In this case, we decompose in three domains. Update each domain with different time step with the interval coefficient n. Simulation is started from the largest time step domain and then go to the smaller time step domains. Smaller time step domains are advanced n times, and as a result of this method, we can reduce the whole runtime of the simulation. These are the result video of our method for rain scene. Left is a standard transparent rendering view, and right is the visualization of the computed level. Blue is advanced with largest time step, and yellow and red domains are computed with 1/3 and 1/9 time step compared with blue region. As you can see, there are no visual discrepancy of the boundary where advanced with different time step. This scene runs 6.46 times faster than the synchronous method. I will introduce you about our method in this presentation. Before talking about our method, let me introduce the background of liquid simulation. To simulate liquid, we have to discretize the simulation domain. There are two common approaches for discretization, Eulerian and Lagrangian. In Eulerian method, we split the simulation domain into grids and set physical values like velocity or pressure on the cell center or cell faces. We refer to the adjacent state value for calculation. The other one is Lagrangian method. In this method, liquid is considered as the aggregation of the particles. When we calculate the values on the particle such as velocity or pressure, we use the values or distance from the particles around it. Today, we focus on the Eulerian method. It is said to be unconditionally stable of the time step sizes. Of course, using large time step to advance can reduce the total runtime of the simulation, but also it leads to the low visual quality because it neglects the details such as splashes. So in fact, we choose a time step by the CFL condition. The CFL condition originally means that liquid shouldn't travel more than the size of a cell width within a single time step. In computational graphics, we use the right-hand side coefficient C equal around 2. It is good from a perspective of the balance of visual quality and computing efficiency. Hereafter, we call C as the CFL number. If CFL number is large, some details are neglected as we just mentioned. Moreover, the simulation is suffered from noisy artifact as this video shows. Even though this is a static pool scene, computing with a large time step induces noisy perturbation on the CAM surface. On the other hand, if the CFL number is small, the simulation will be inefficient and suffer from numerical diffusion like energy dumping. So CFL number should be neither too large nor too small. Because we can't control the velocity, we must choose adequate time step to satisfy this condition. To solve such a problem, several related works have been proposed. The state-of-the-art method for Eulerian is the global adaptive time step method. They determine time step not constant but adaptive in each step by the maximum velocity in simulation domain to satisfy the CFL condition. For example, decide delta t1 at the first time step and advance all region with it. In the next step, we estimate time step delta t2 and advance again, and continue this strategy. Since they decide time step from the maximum velocity, all regions satisfy the CFL condition. However, because this method based on the maximum velocity, the majority part of the liquid, such as green-colored cells, has small CFL number when there presents a large variance of velocity magnitude. This is undesirable in terms of the computational efficiency and numerical diffusion. Other approach is for material point method, which is one of the Lagrangian method. They use asynchronous time step to advance instead of the global time step. With asynchronous time step, they assign different time steps for each region. For example, the figure is that fast balls impact on the dragon scene. Around the dragon's head, where has small velocity, is advanced with large time step, and near the fast ball uses small time step because the region includes so fast-moving particles. However, such asynchronous methods haven't well researched for Eulerian method. So we researched about the Eulerian method that simulate with different time step piece by piece, so to speak, asynchronous Eulerian liquid simulation. For asynchronous simulation, we have to decompose the simulation domain. Each subdomain is called as level and advanced with different time step. We use the same delta t0 as the time step size for the global time stepping method. So we compute it by the maximum velocity. Using time step become bigger with the integral coefficient n. We decompose simulation domain in 3 steps. At first, label the cells based on the velocity on the cell. Labeling threshold is determined to make CFL numbers in each level less than the target number. After that, we consider the pathway of the liquid in the cell, which is labeled to use small time step. Finally, expand level domains from smaller to larger. In our examples, we expand 6 cells wide empirically. Later 2 steps are added to minimize the loss of visual features such as the sudden emergence of the splashes. Going through these steps, domain decomposition will be completed. Next is about the time integration. This figure illustrates 1D simulation for the ease. Each block represents a cell. With synchronous method, the amount of computation is related to the number of blocks. However, once domain is decomposed with the interval coefficient n equal 2, we can reduce the computational cost as illustrated here. For asynchronous method, simulation starts from the largest level. At this moment, the target cells involve the domains with the smaller level. Then we can get the state at the time of 4 delta t0. Next, we calculate one smaller level with 2 delta t0. It also involves the smaller level cells. When computing pressures also, we need boundary values at this time. So we interpolate the values from the state of t equals 0 and t equals 4 delta t0 and specify as Dirichlet boundary condition. The spatial interpolation is done with asynchronous advection we will mention later, and the temporal interpolation depends on what kind of quantity such as velocity, pressure, and level set. After that, calculate one more smaller level with delta t0. At this moment, we interpolate values from the result of previous level like the blocks colored as blue or yellow. In this example, this level is the smallest, so advance then again and overwrite the result computed with 2 delta t0. Then we can get the state at the time of 2 delta t0. As all target cells of the yellow level are updated to delta t0, then we compute this level with the same strategies. Simulation flow after here is the same as I mentioned. All remaining cells are recursively calculated and overwritten by the result of smaller level. And when all cells are updated for delta t0, then we proceed to the next step. When we want to interpolate values, it is important to choose the interpolated point in terms of the position or time. Otherwise, visual discrepancy may appear over the boundary of domains which has different time steps. Let us explain this problem with the example of free-falling water drop. For an extreme case, if the domain boundary line exists on the center of the free-falling drop, advance with semi-Lagrangian method introduces visual discrepancy as can be seen in this figure. This problem occurs in following process. In this illustration, the left domain is advanced with 2 delta t0 and the right domain is advanced with delta t0. In naive advection, the movement is calculated with velocity and time step. The velocity is computed as the time-integrated value of acceleration. In this case, the acceleration corresponds to the gravity g. And the position shift of the liquid is computed as the time-integrated value of velocity. So the velocity on the left side is 2g delta t0 and the position is calculated by multiplying this with the time step. So it moves like this animation. On the other hand, velocity on the right side changes from g delta t to 2g delta t0. So the total amount of shift will be the sum of them and moves as the figure illustrates. As a result, visual discrepancy appears in the boundary of domains. To solve this problem, we additionally modified this advection in our method. Our approach is to fix the advection of large time step to that of small time step. To do this, we use acceleration. Movement in small step is written as the sum of the movement in each step. So, for the large time step advection, we apply same strategy. Velocity we use is accelerated in each step, and the movement on the large step is written as this. By this modification, the total movement will be compensated and corrected. As a result, both sides of liquid falls almost equivalently. These are the results. The left figure is advected with naive advection, and the right one is advected with our method. As you can see, we succeeded in preventing the visual discrepancy. Next, we provide the details of interpolation, which consists of spatial and temporal interpolation. At first, we explain about the spatial interpolation. Spatial interpolation is related to the advection scheme, so we backtrace the position with our improved asynchronous advection scheme and use the values located there for the next step. Next, let me explain about the temporal interpolation. We use different interpolation schemes depending on fluid attributes. For velocity interpolation, we use the velocity at the backtraced position and accelerate it to use in each step. Next is interpolation of the level set, which is the signed distance function. The advection of level set represents the shift of liquid, so we use the level set values at t equals 0. The position is backtraced with our improved advection scheme. Finally, for pressure interpolation, we use the values already updated because the pressure represents the average of pressure between two steps, not exactly a quantity at a specific time, and set the interpolated values as secret boundary condition to calculate the smaller level domains. From here, we show you the result videos created by using our method and compared to Synchronous method. The computational level will be visualized in the result we further show. The blue part uses the largest time step, yellow and red are advanced with 1/3 and 1/9 time step of blue respectively. The first result is about rain scene, already showed at the beginning of this presentation. Falling raindrops has large velocity and the large portion of liquid below has velocity almost zero. This is comparison. In this ideal scenario, synchronous method takes 337 seconds per frame, but our method takes only 52 seconds per frame. So our method runs 6.46 times faster than the synchronous result. The next result will be splicing. In this case, most of the liquid moves dynamically and less regions are computed using large time step. You can see that the yellow and red parts are dominant in this result. However, our method still can reduce the total runtime and speed up 2.85 times without minimal loss of visual quality. The last one will be about breaking down scene. This scene is different from last two scenes at the point that the maximum velocity becomes slower and slower as the time simulation proceeds. So as it goes to the end of simulation, the advantage of the asynchronous method becomes small. But in such a scene, which might be thought unsuitable for our method, we even succeeded in speeding up of 2.05 times faster. Specifically, our method runs 88 seconds per frame, and the synchronous method takes 180 seconds per frame. Next, let's rethink about kinetic energy of the breaking down scene. In this graph, blue line is the result of synchronous method and red line is the result of asynchronous method. We can see that the kinetic energy of the asynchronous method is larger in the end of simulation. It is because we use time step with adequate CFL number for every domains with our domain decomposition method. This result indicates that we can reduce the numerical diffusion of velocity and improve kinetic energy. At last, let's discuss about our method. This graph illustrates the computational time per frame for the video scene. Generally, our method improves the computational runtime of the simulation. In details, our method works well in the scene like rain, where we get the largest reducing rate in our examples. And for breaking down scene, our method can reduce the computational runtime, but however, its scale is not as large as the rain scene. It is because the scene do not contain large variance of velocity magnitude. In this sense, we can say that our method reduces computational runtime. The reducing rate is large in the scene with large variance of velocity, and for the scene without it, simulation runtime can be reduced, but the degree becomes smaller. In conclusion, our method is asynchronous Eulerian liquid simulation. We advance decomposed simulation domain with different time steps, and interpolate from the previous time level to specify the delicate boundary conditions by asynchronous advection. As a result, we succeeded in reducing the runtime largely when the variance of velocity magnitude is high, and our method also improves the kinetic energy preservation. In the future, we want to apply our method to smoke or two-way coupled rigid bodied simulation, or combine with more accurate methods such as flip, epic, or McCormack advection. Thank you for listening.
All right, thank you very much for the talk. So we have some time for questions now. I will start by asking you, can you tell us more about why each of these quantities are treated differently during advection? So you had different strategies for how to sample the pressure during advection or when to do the velocity. That was sort of brief in the talk. I'd be happy to hear more about that. Can you hear me?
Oh, sorry, it's howling. Please question.
I'll repeat the question. Okay.
Again.
So in the talk, you talked about how different quantities are treated differently when being advected. And so, for example, the pressure was treated slightly differently than the velocity, and I thought that was quite interesting. Can you please elaborate on that?
Sorry, sound is multiplying, so I can't listen you. Sorry.
Okay.
You can please give me the text question.
Sure, I can do that. Okay, one moment.
Sorry.
Maybe I can get a more concise question really quickly. Okay, so I will switch the question to a simpler one, which is about any ideas for using this in a Lagrangian technique instead of Eulerian. So, do you have any ideas on how to apply? Let's see. This to flip.
Any ideas how to apply this to a flip? Okay. To apply to flip, I think it is. We can combine with it and to apply to flip. We use advection scheme of our method, and maybe I think the domain decomposition is also works on the flip. So maybe I believe it is works on the flip.
Okay. That's okay. Yeah.
Yeah.
So one more question. Do you still have trouble hearing me?
Yeah, now it's trouble.
It's a little better now?
No.
No, okay.
Sorry.
It's okay. So I will ask my first question again. I'll write it into the chat to see if I can do this quickly. So the question was how we, in the talk, he talks about treating pressure and velocity different during advection, and I'm asking him to reply to this.
Oh, it's because each quantity for pressure, we think pressure is not a specific time value, and average, we think it is average value in the time step. And for velocity, we have to accelerate it in the velocity time step to use for the boundary values. And for the level set, we don't interpolate and use values at the time t equals 0. So it is because our asynchronous advection method works as advection method on synchronous, like synchronous method.
Okay, I think this is great. I believe we can move on to the next talk now. So thank you very much. I appreciate the talk.
Sorry.
It's no problem. So the next talk will be local bases for model-reduced smoke simulations, and the speaker will be Olivier Mercier. He should probably say his. Well, I guess when we get to the question and answer, he will say his name better, because I'm sure I'm butchering everybody's names. Okay, so let's get on with the show. Thanks.
Hi everybody, my name is Olivier Mercier, and this is work I did with Derek Now Rosezaray as part of my PhD at the University of Montreal. So this work is about the simulation of incompressible fluids, but we focus specifically on smoke simulations. And it's a fairly mature field of computer graphics. It's been around for more than 20 years now. But in this work, we propose a new method for the simulation of smoke. So a very common framework for smoke simulation is to use a grid that covers the simulation domain that we care about. And on this grid, we store the velocity of the fluid, and then we use particles to represent the smoke, and these particles are just passively advected by the velocity that we have on the grid. And then we update this velocity at each time step using the Navier-Stokes equations that I'm showing here. This method of using particles in a grid is used by many well-established methods, like the flip method, for instance. And I guess I should say I'm being a bit sloppy with my math here. I'm actually omitting a few constants in the Navier-Stokes equations for density and viscosity, and I'm doing that for simplicity since it doesn't really change the exposition of the method, so I apologize for that. So the first part of the Navier-Stokes equations are basically the F equals ma for fluids, and it gives you the instantaneous change in velocity. And then the second part here is the incompressibility constraint, and this constraint basically prevents the velocity from compressing the fluid, so the velocity cannot have any sinks or sources, and the fluid is only allowed to sort of swirl around like it does in real life. So this approach of using a velocity grid works quite well, and here's a simulation example. Here I'm simulating two vortices interacting with each other, and I'm visualizing the vorticity of the fluid just so we can track the vortices more easily. And as you can see, as the fluid evolves, there are a lot of complex interactions and finer structures develop over time. And so after a while, we end up with details at many scales throughout the domain. And so using a grid that is fine enough to resolve all of those small details everywhere at the same time in the domain can become very costly. So we want to use a representation that is more efficient. Now, one class of method that can achieve that is called the model reduction approach. The idea here is to use a set of basis functions and to restrict the velocity field to be a linear combination of these basis functions. So the complexity here is now only determined by the number of basis functions that we use. And the difficulty, of course, is now to choose the right set of basis functions that will generate the fluid simulation that we want. So one approach suggested by Treuil et al. Is to use snapshots of a full grid simulation as our basis. This is nice because it makes sure that the velocity fields that we use in the basis sort of make sense for the simulation domain that we have. But it also means that we need to pre-compute a full-scale simulation to create the basis. So it sort of defeats the purpose a little bit. A second approach proposed by DeWitt et al. Is to create the basis functions from the eigenvectors of the Laplace operator on the domain. And this can generate a set of basis functions analytically without any pre-simulation, which is nice. And it gives a basis that is like a Fourier basis, but for velocity fields. And the basis functions can be created at various frequency and various scales. And they have repeating patterns, just like a Fourier basis, really. Now, if the basis has nice properties, it can also make the math of the simulation a lot easier to handle. First of all, if the basis functions that we use are divergence-free, which is the case for the two bases that I just described, then we can get rid of the divergence-free constraint in the Navier-Stokes equations because it's now automatically baked into the basis functions themselves. And the pressure term can also be eliminated, and this is extremely useful since these are the two most expensive parts of the simulation in a traditional fluid solver. And then we can take the remaining equations, which are defined in terms of the full simulation space, and we project them onto the basis coefficients directly. So all the simulation behavior is now expressed in terms of operators that act on the basis coefficients only. So we almost don't need to care about the simulation space at all, we just work with the coefficients of the basis functions. So if I choose to work with, say, 3 basis functions, then the whole system of equations can be written as a system in R3. But of course, the more basis functions we use, and the more interesting the velocity field will be, so you definitely want to use more than 3 basis functions. Maybe a few hundreds can work, but usually we can get satisfying simulations with a relatively low number of basis functions, and that's the whole idea of the model reduction, really. In the projected equation, I highlighted one term in green that is a matrix that we need to invert, and that can be a costly operation. However, if our basis is orthogonal, then this term is just the identity matrix and we can remove it completely. So having a basis that is orthogonal is another very nice property to have. And we'll come back to that later. Now, in our work, we propose to have a new basis for smoke simulation, and our basis has one additional property, that is that its elements have a finite support. Now, if I go back to the previous slide, we see that these basis functions extend over the entire domain, whereas what we propose is to instead have basis elements that are contained in a small region. So our goal is to create a basis function that represents sort of a small vortex structure at a given scale, and then we want to copy this basis function in a regular grid pattern to cover the whole simulation domain. And we want to also be able to scale this vortex in x and y independently, so we can cover the domain at different scale and different anisotropy ratios. Having this finite support for each basis function has many advantages. First of all, it sort of gives meaning to the coefficients of the basis, since we know that changing the coefficient of one of the basis functions will only have an effect on a given region and a given scale of the simulation. So it gives us a lot of intuitive control over the simulation. It also allows us to be more intelligent in the way that we cover the simulation domain. So if we have a simulation domain with a weird shape, which is often the case in practice, then we can decide to cover it non-uniformly. We can use coarse basis functions in the bulk of the simulation domain, and only use finer basis functions in the more narrow parts of the domain and around the edges. This allows us to decide where we want to put our simulation details, and it reduces the total number of basis functions we need to use, so it reduces computation time in the end. We may also want to put coarse basis functions everywhere, but only place the finer elements closer to the camera, since this is where the user is more likely to see the finer details in the fluid. So having basis functions that are localized in space generally allows for more control over the way that we build the simulation space. So if we summarize the basis properties that we want a basis that is divergence-free to simplify the Navier-Stokes equations, that is orthogonal to remove the matrix inverse in the projected equations, and we want basis functions with local support to give us more flexibility and control. And additionally, we want a basis that is complete, by which we mean that we want to be able to generate as many basis elements as we want. So for instance, if we compare the basis I presented before with respect to these four properties, first, the basis of Troy et al. Is divergence-free, but it's not naturally orthogonal, although it can be made orthogonal with some additional work. It doesn't have local support because each element extends over the entire domain. And it's not complete according to our definition because we cannot easily generate more basis elements on the fly. So if we want to add more basis elements, then we need to generate a longer simulation sequence and take more screenshots, which is not really trivial to do. In comparison, the basis of DeWitt et al. Is complete because it can analytically generate as many basis elements as we want without any additional precomputation. Looking at these properties, a wavelet basis might also look like a good option, but it's actually provably impossible to generate a wavelet basis that satisfies all four properties with the usual wavelet approach. So the goal of our work is to generate a basis that gives us a better compromise between these four properties. The basis that we'll construct is divergence-free and it has local support, but we make some compromises on orthogonality and completeness that we think are well suited for fluid simulations. Okay, so how do we construct this novel basis? Well, we start with the eigenvectors of the Laplace operator on a square domain, much like DeWitt et al. Did in their work, but we want to isolate the central region in this vector field, because this region has pretty much everything that we want. It's divergence-free because the eigenvectors are divergence-free, and it has the right sort of vortex shape that we're looking for. So we only need to make the support of this vector field finite. However, just clamping it outside of 0, outside of the red square, just creates a discontinuous vector field, which is obviously not natural and not what we want. So instead, we try to combine multiple eigenvectors together. If we look at the eigenvectors with frequency 1, 1 and 1, 3, we see that changing the y frequency here only changes the vector field in the y direction, really. But the vectors in the region indicated by the red arrows remain exactly the same as they are in the 1, 1 frequency. So what we can do is we can subtract both eigenvectors with the right scaling, and that will zero out the vector field along these horizontal lines here. And then by repeating the process in the x direction, we're able to completely zero out the vector field along the red square boundary. And then we can clamp that vector field to 0 outside of this region and it remains continuous. And this process also works with different frequencies and weights to create these vortices at different sizes and different anisotropy ratios. Now, we can formalize this process a bit instead of just guessing the coefficients that we need in that sum. So we're looking at linear combinations of 4 eigenvectors, b11, b31, b13, and b33. And we have the constraint that we want the resulting vector field to be 0 on the boundary of this red square region. And we also want the coefficients to not all be zeros, otherwise the vector field is just 0 and that's not interesting. So we show in the paper that this can be solved as a linear system, and then the set of coefficients that we find gives us the basis function that we just created in the previous slides. But this vector field is still not perfect because it doesn't create an orthogonal basis. In our case, orthogonality really means that if we take two different basis functions in the basis, the integral of their dot products should be 0. So we could simply position the elements in the simulation domain so that they never overlap, and that would create a trivially orthogonal basis, but then the coverage of the simulation domain would be very poor, and it would be leaving large regions of zero flows everywhere, so it's not very interesting. So the basis elements need to overlap somehow, and in this case, the basis functions that we created are just not orthogonal at all. However, orthogonality is really just one more constraint that we can add in the construction that we just used. So instead of looking at linear combinations of 4 eigenvectors, we can add more terms to the sum and go up to 9 terms, and then just add the constraint that each basis element needs to be orthogonal to each of its 8 neighbors. And it turns out that we can still solve this problem, and we find weights that now satisfy the orthogonality condition as well. And the new basis function that we create looks something like this. And once again, we can repeat the process at different anisotropy ratios and different scales. So we end up with a basis that has the orthogonality properties baked directly into the basis elements. And the orthogonality property is not perfect really here because we're only looking at orthogonality within a single frequency layer and not across different frequency layers. So large basis elements won't necessarily be orthogonal with smaller basis elements, for instance. But still, this partial orthogonality that we give to the basis, it gives us a way to parallelize some of the computations and to speed up the simulation. And the basis elements can also be scaled, so we really only need to compute these basis elements once for each anisotropy ratio. And then we can use them as sort of templates that we can copy throughout the domain at different scales. So even though these basis functions that we create are a bit more costly to evaluate, we can just pre-compute them once, store them in a high-resolution lookup table, and then all further basis evaluations are just table lookups, which is relatively efficient. And this whole process also extends to 3D, and we give the details of the 3D construction in the paper and in the supplementary material. So now that we have constructed this new basis, let's see how we use it to simulate fluid dynamics. So if we go back to the projected Navier-Stokes equations, we see that a lot of the work is contained in the advection tensor A and this diffusion matrix D. And the tensor A is especially cumbersome, and you can see here what its terms look like. Each term in that tensor represents the effect of one basis element being deformed by another, and then the result of that is projected onto yet another basis element. So that means working with this tensor means we need to take into account all possible overlapping triplets of basis functions. And this is a lot of elements to take into account, and it can become really, really expensive. So instead of exactly solving these projected Navier-Stokes equations, we decide to take a more heuristic approach. So we focus on recreating the main parts of the energy cascade. Now, the energy cascade is this concept in fluid dynamics that describes the evolution of a fluid in the regime where turbulence is fully developed. So basically it gives a relation between the size of elements in the fluid and their energy. And there are 4 components in this energy cascade that we want to recreate. First, energy can enter the system from some external means. Then energy can be transported within a frequency layer. Energy can also be transferred between frequency layers from larger structures into finer structures. And then finally, energy can be dissipated at the finer levels. So let's put that in context with the same simulation example that we used previously. Here, the initial energy simply comes from the initial conditions of the simulation. There's energy in these two vortices that I put in the simulation. And then at the beginning of the simulation, these two vortices mostly move around each other, but they don't really change their size too much. So that's really just transporting energy within the same frequency layer. But eventually they will decay into smaller and smaller structures, and now that's transferring energy across different frequency layers. And eventually the structures are small enough that they just dissipate into the simulation. And here, these wispy trails, for instance, don't contribute anything to the simulation anymore. Their energy is just gone. So these four behaviors is what we want to replicate in our fluid simulation. So first we simulate the transport part. Now this would be relatively easy to do if the basis functions could move inside of the domain. If we wanted to compute the effect of the green element over the red element, then we could simply integrate the green vector field over the support of the red element, and that would give us a movement direction, and we could just move that basis element forward by some time step. And if we have multiple elements, then we could just sum the influence of all these neighboring elements to compute this movement direction. But our basis elements are fixed in space and they cannot move. But we still compute this movement direction for each basis element, and we look at where they would be moving if they could move. And this gives us some sort of virtual new location for each basis element, and then we take the energy of that basis element and transfer it to the nearest basis element around this new virtual location. And we give some justification in the paper as to how we can do this using just some simple interpolation. Now, because basis functions are always at the same spot at each frame of the simulation, we can pre-compute all of these Tij factors here, so we don't need to recompute the integrals at each time step. So this makes the update scheme simple and efficient to compute. So this gives us a way to mimic the transport dynamics. And now for the energy transfer between the frequency layers, we again try to replicate the behavior of the energy cascade. So we organize the frequency layers in a graph like this, and at each time step we transfer some of the energy from the coarser layers towards the finer layers. And we can do this by taking some portion of each basis coefficient and transferring it directly to its smaller neighbors. Energy can also enter the system from external forces, like from initial conditions, or from buoyancy forces generated by the smoke particles, for instance. And energy can also be dissipated at the finest levels by just removing energy from the system instead of transferring it to other basis elements. And we use this energy transfer scheme in a way that approximates the energy cascade of real fluids, so that the behavior of this energy transfer is as realistic as possible. So by combining the transport and transfer strategies, we get convincing fluid behavior. We can see here that the smoke plume is able to rise and decay into finer turbulent structures. And our energy transfer strategy can also be tweaked if we want to. So we can change some of its parameters to move away from the usual energy cascade behavior, and this gives us some control over the look and the behavior of the overall simulation. Of course, we are using a model reduction approach here, and we're using a lot of heuristics in our fluid dynamics. So we are not solving the Navier-Stokes equations directly, and our simulation will not look exactly the same as a full space grid simulation. Here we compare a smoke plume computed with a grid method on the left and with our method on the right. And the behavior is different, but we are still able to recreate most of the visual features of the simulation. We're able, for instance, to generate these smaller vortices that appear on the side of the smoke plume, and this is all very important to recreate the overall look of the simulation. If we look again at the example I showed at the beginning of this presentation, we see that the smoke plume evolves with the behavior and the appearance that we expect, and we also show in the paper how we can interact with mesh obstacles so that the smoke is able to wrap around the bunny in this example. In this other example, we use the coverage strategy that we discussed earlier, where we place the basis elements non-uniformly inside of the bunny. So we place fine basis elements in the ears of the bunny so the smoke can properly reach and cover these narrower regions. But in the bulk of the bunny's body, we use mostly coarse basis elements because the geometry is simpler there, and we don't need to have as much smoke details. In this example, the adaptive coverage strategy reduces the number of total basis elements by 1 order of magnitude, so it saves a lot of computation time. We also show in the paper how we can interact with dynamic obstacles. So the idea is to project the motion of the obstacle boundary onto our basis. So we take the normal velocity field of the obstacle, and we also put additional basis elements in the simulation just to represent the object's motion. And then by projecting the normal velocity field onto these additional basis elements, we create a vector field that approximates the object's motion, but is also divergence free. So with this strategy, we can interact with any dynamic obstacle. And the code for this 2D simulation is available online if you want to play with it. This, of course, also works in 3D, so in this case we can move the hand through the smoke cloud and the smoke is nicely pushed around and can also move through the space between the fingers. That's it for my presentation. If you have any questions or you want to check the source code, you can visit my website or feel free to send me an email. Thank you.
Thank you very much for the excellent talk. So we have time for questions now, and I realize I missed some questions in the YouTube channel before, so please feel free to actually ask questions there. I will pay attention, assuming I don't have more technical problems. So for now, I will ask a question. So thanks for the talk, Olivier. Can you talk a bit more about I'll ask my question first. So do you have any thoughts on how to modify the basis in the middle of the simulation? So for example, if you really wanted adaptive refinement around a moving obstacle, you might have to selectively add and remove bases. Do you have any thoughts on how to do this efficiently?
Sure. Well, in the paper we show that you can stretch those basis elements around a moving obstacle to sort of like go around curved boundaries and stuff like that. That's still using a lot of heuristics, so that we pre-compute all of the interaction between the basis elements is all pre-computed. But then if you distort one of the elements, you would technically need to recompute these interactions. We don't do that, and we sort of try to get away with it. It's not super clean. Because if you insert a new element in the simulation with a different shape, then you need to compute an integral of the vector field in real time, which is going to be costly. Maybe like if it's a rigid obstacle, for instance, and say it's not rotating or anything, maybe you could pre-compute a set of basis elements and just pre-compute the interaction of these special bases with your regular basis. Maybe you could do something there. But what we've tried really, the easiest solution was just to stretch those bases and assume that the interaction would be the same.
Thank you. One more question. Have you thought about optimizing this basis? So you showed an example where you compared your method to an existing implementation of stable fluids, for example. And I imagine that you could like super saturate the basis and then say, well, I want to just pick only the ones that will make this particular style as close as possible, or something like this, where you could sort of use an optimization to select a basis. Have you thought about anything like this? Like
definitely, yeah. We tried, because we found one basis basically in two dimension that's using a sum of 9 eigenvectors. So that gives you just enough degrees of freedom to get the orthogonality property. If you add more degrees of freedom, then you can add you can continue adding eigenvectors and add any sort of property you want. But it gets a little bit difficult to control. So if you go like one step further and use 16 eigenvectors, then the basis element that you get starts to have a lot of high frequency in it. And so the simulation doesn't look as natural. Like it's really helpful visually if your basis element has the shape of a vortex at that scale. Otherwise, the coarser elements will also have an influence at the larger scale, just because they also contain higher frequencies in there. So we could not find any good basis element to solve any sort of additional visual properties or any additional like physical properties. But we hope it can be done. Like there are definitely other basis elements like that you can create, and hopefully you can tailor these basis elements a little bit more.
Great. Okay, and then we'll take one more question from the audience. So Christopher Brandt asks, if I understand correctly, you only use a reduced basis for the Eulerian velocity field. Do you think using a reduced basis for the particle positions as well might help?
If you can combine the two bases together, yes. The more expensive part of our current implementation is we're naively going from reduced space to full space to compute the particle advection, which is very, very costly. Yeah, if you could have some basis for the particles themselves, it would be useful. But if you had sort of two different spaces, if I'm understanding the question correctly, if you had two different spaces, one for the velocity and one for the particles themselves, as long as you can go between the two, I assume you can get something that's more efficient. But I'm not sure how.
Okay. Thank you very much for the talk and for the insightful questions, answers to the questions. So the next paper in the session will be fast and scalable solvers for the fluid pressure equations with separating solid boundary conditions, and the speaker will be Junyu Lai.
This presentation, I will talk about fast and scalable solvers for pressure equations with separating solid boundary conditions. Firstly, I will describe the background of fluid simulation and explain why separating solid boundary conditions is necessary. As we can see from this video, the simulation on the right uses the separating solid boundary conditions, and the fluid does not stick to the boundary. Then I will illustrate the formulation of the linear complementarity problem from such conditions. To solve this problem, we propose three methods: pole situation, penalty method, and the full approximation scheme multigrid. Finally, I will present the numerical results in different fluid simulation scenarios. The fluid simulation is modeled by the incompressible Euler equations. The solving process is split into three components: adding the body forces such as gravity, solving the pressure equation, which is the most time-consuming part and the main focus of this presentation, and the advection. For the discretization, we adopted the standard staggered grid layout, where the velocity normal components are on cell faces and the pressure are at the cell centers. We classify the cells into different types. For example, in this 2D half-fluid scenario, the red cells are fully inside the liquid, and the green cells fall in both liquid and solid. We will come back later regarding how to handle different cells when solving the pressure equation. At the nth time step, we obtain U hat after applying the body force and proceed to the pressure equation. When it comes to the boundary, the standard boundary condition causes the fluid to stick to the boundary as shown in the left figure, which is considered unrealistic. Therefore, the separating solid boundary conditions are proposed to deal with it. This means either the fluid is moving away from the wall, or there is a pressure force acting to prevent it from entering the wall. After integrating the divergence U, we eventually formulate a new pressure equation with separating solid boundary conditions. This is also known as linear complementarity problem. As the separating solid boundary conditions are enforced on the boundary only, we solve the LCP at gray cells, which fall in both liquid and solid. Several solvers are proposed to solve the LCP from this fluid simulation. The path solver, which is a generalization of the classical Newton's method and based on quadratic programming, is used by Betty when he introduced the separating solid boundary conditions. However, the path solver cannot scale to large problems. Two other methods are proposed recently. One is a multigrid by Chetnet's Ada, which is based on the standard multigrid for linear problems. However, Using a linear multigrid to solve the nonlinear LCP is not a very accurate approach, and the scalability of the method is not clear yet. The other method is the minimal map Newton's method by Anderson et al., which uses the Newton's method to find the solution to the minimal map function. However, each Newton iteration requires complicated formulation of the linear system and the line search. Therefore, we propose scalable and fast solvers to address these issues. Instead of dealing with the LCP directly, we derive the equation by introducing a sequence of optimal controls lambda I, which are either 0 or 1. When lambda I is 0, the fluid moves away from the wall, otherwise the pressure is positive, so that it prevents the fluid from entering the solid boundary. This equation is known as an Hamilton-Jacobi-Bellman-HJB equation. To write the HJB equation in the matrix form, we define the set of control matrices, which are diagonal matrices with its entries be either 0 or 1. Here, for grid cells, lambda is undetermined because the constraints are enforced and makes it an LCP problem. For other cells, we let lambda be 1, as no constraints are enforced on them. We propose three methods to solve this equivalent HJB equation. Our solvers include the precipitation penalty method and the full approximation scheme multigrid. As we can see, the two unknowns, the pressure and the control matrix, are coupled with each other. The idea of precipitation is to fix either one of them, which allows us to solve the other one. For example, we fix the pressure, and we can determine the porosity lambda I for the loads corresponding to the boundary cells in order to produce the minimum value. Then we can evaluate the new pressure with the updated porosity. We alternate between the porosity evaluation and the porosity improvement until convergence. To solve our HJB equation, we treat the control matrix as the porosity. When we fix the porosity, we formulate a linear system and solve it for new pressure. To solve the linear system, we have the option of using preconditioned conjugate gradient (PCG) and multigrid, which I will talk about later. The penalty method enforces the constraints implicitly by adding a large penalty term in case of constraint violation. It aims to solve this penalized nonlinear equation, which is numerically equivalent to the original LCP. If the pressure is positive, it satisfies the linear equation. Otherwise, its value has to be very close to 0 due to the large penalty term. Introducing the control matrix lambda, we write this equation into an HJB equation in the matrix form, so we can solve it using the porosity iteration. Like the porosity iteration, the penalty method also requires solving a linear system in each iteration. The solver can be either PCG or multigrid. The idea of multigrid is to remove the high frequency error on the fine grid and deal with low frequency error on coarse grid as it is cheaper. As we can see in the diagram, we smooth the error and restrict it into the coarse grid and solve the error equation. Then we interpolate the coarse grid error back to the fine grid and use it to collect the fine grid solution. This process can be done recursively, so that we only solve the equation exactly on the coarsest grid. There are several ways to do the multigrid. One way is to perform the V-cycle, which is to recursively go straight to the coarsest level, solve the equation exactly, and then come back to the finest level. The other way is called full cycle multigrid FMG, which firstly obtain a better initial guess from the coarse grid before performing the V-cycle. Therefore, it starts from the coarsest level and involves doing several V-cycles. For our multi-grid solvers, we use the V-cycle only as we consider it is cheaper. As the problem we are solving is non-linear, we use the full approximation scheme multi-grid, which is different from the linear one. We use the projective Gaussian as the smoother at the fine level and the solver at the coarsest level. On the fine grid, because the operator n is non-linear, the Euler equation may not hold, and we cannot restrict the Euler equation into the coarse level directly. Solving the Euler equation directly may result in very inaccurate fine grid collection. Instead, we restrict both the solution and the residual into the coarse grid. We obtain the coarse grid Euler by subtracting the restriction of the fine grid solution from the coarse grid solution. Then, we interpolate the Euler back to the fine grid and perform the collection. Here, the formulas highlighted as red indicate the differences from the linear multigrid. The right-hand side, H, contains both the restriction of the residual and the coarse grid operator applying to the restriction of the fine grid solution. To compute the coarse grid matrix, one way is to formulate the matrix with a direct discretization on the coarse grid, which is cheap. However, due to the complexity of the free simulation, the matrix may not be accurate to ensure a good convergence. To address this issue, we construct the matrix using Galerkin method. The matrix is computed by multiplying restriction operator from the left and the interpolation operator from the right. This is more expensive, but renders a more accurate matrix, which facilitates the convergence of the multigrid. The bilinear in 2D and the trilinear in 3D use all surrounding points for interpolation and are more accurate than the piecewise constant. However, the dense interpolation and the restriction operators can make the construction of the coarse grid matrix expensive. Therefore, we propose the barycentric interpolation and restriction, which only uses the closest surrounding grid points while keeping the same order of accuracy. We can see that in 2D we use 3 instead of 4, and in 3D we use 4 instead of 8, which makes the operator much sparser. Especially in 3D, we can get a matrix that is twice sparser. Here is an example for computing the coarse grid matrix from 8-cube grid to 4-cube grid in 3D. The coarse grid matrix from using trilinear interpolation is almost twice denser than using barycentric interpolation. This is because the interpolation operator for trilinear is almost twice denser than the barycentric. Our experiment shows that using a barycentric interpolation and restriction can speed up the computation greatly, especially for large problems. For the interpolation near the boundary, we notice that there are jumps due to the constraints being enforced on the boundary only. As we can see in this 1D example, the interpolation shown as a blue dotted line uses the points that are both inside and outside the boundary, which gives an inaccurate value. If we remove the points outside the boundary, we can get a more accurate interpolation, which is shown as the red line. To deal with this, we modify the interpolation by taking these points away and rescaling the weights. For example, in this 2D grid, the barycentric interpolation requires the point 1, 2, and 3, but we take away the point 2 because it is outside the boundary. We test our solvers in 3 scenarios in 3D. The first one is a half fluid inside a solid sphere. The second one is also a half fluid, but with a solid cuboid inside. The third one has a solid outer boundary created as a union of two spheres. The two hollow solid spheres are also placed inside the domain with the bottom one having holes through it. We compare our methods with the two existing methods. The multigrid by Chatterton's ADA uses full cycle and constructs the coarse-grid matrix through direct discretization. Instead of using FAS, their multigrid is based on the linear version. Another method to compare is the Newton's method. Like our polarization and penalty method, it also requires solving a linear system in each iteration, but has complicated formulation of the linear system. All methods include the FAS multigrid, polarization, and penalty method with PCG or linear multigrid as the linear solver. For scenario 1, the number of iterations for FSMG, the polarization and the penalty method with multigrid remains almost constant. For other methods, the number of iterations double with the problem size. For scenario 2 and 3, which are more complicated, the FSMG keeps the same scalability, while the polarization and the penalty method with multigrid scale worse. They scale slightly worse than the FMG in scenario 2, but better in scenario 3. Compared with Newton's method, either using multigrid or PCG, the polarization and the penalty method scale better in both scenarios. Based on the results, we conclude that FASMG scales the best. The polarization and the penalty method with multigrid scale worse, but in general better than FMG. The polarization and the penalty method with PCG also scale slightly better than the Newton's method. We test all solvers, including the non-LCP solver, for 100 frames for scenario 1 in both 2D and 3D, and measure the average time per partial equation. In 2D, the FSMG, the polarization, and the penalty method have very similar performance, but are much faster than the FMG and the Newton's method. In 3D, up to the size of 128, the FSMG in general performs almost the same as the polarization and the penalty method. However, at the size of 256, the FSMG can be twice faster than the polarization and the penalty method. The non-LCP solver is much faster than the other methods when the problem size is small. However, at the size of 256, the FSMG is only slightly slower in both 2D and 3D. In conclusion, for almost all cases, the FSMG is the fastest LCP solver. For large problem size, the FSMG is much faster than the polarization and the penalty method, and it is only slightly slower than the non-LCP solver. The test results show that all solvers are much faster than the existing approaches. We compare the convergence behavior for multigrid solvers, the FASMG, the polarization and the penalty method with multigrid, and the FMG. We present the residual versus the number of iterations for each scenario. For scenario 1, the FASMG, the polarization, and the penalty method have similar convergence behavior and are much better than FMG. For scenario 2, the FASMG has similar convergence, but the polarization and the penalty method becomes worse. They perform worse than the FMG at the beginning, but eventually converge faster than FMG. For scenario 3, The convergence result is similar to scenario 1, except that the precipitation and the penalty method have better convergence. From the convergence plots, it is clear that the FSMG has much better convergence than the others. In conclusion, we propose three methods: the FSMG, the precipitation, and the penalty method to solve the LCPs from fluid simulation. We compare our methods with the existing approaches and demonstrate better scalability, timing, and convergence. Our FSMG performs the best because it uses full approximation scheme, value-centric interpolation and restriction, Galeokin approach, and boundary handling. Precipitation and the penalty method also have good performance and are easy for users to implement. This concludes my presentation, and thank you for listening to my talk.
All right, thank you very much for the talk. So we still have time for questions, of course, so please, if you're a member of the audience, add questions into the YouTube, and I'll try to look at them and ask questions if we have time. So to start things off, I'd like to ask you a question about the barycentric interpolation strategy. So instead you have a regular grid, you could use the bilinear, trilinear interpolant, and you made a good case for using barycentric interpolation because it reduces the stencil. I imagine there are some consequences to this, right? You could break symmetry or something. Can you talk a little bit more about what other consequences of using this type of barycentric interpolation aside from the benefits of a smaller stencil?
The consequences is that the convergence is only slightly slower, but it does not break the symmetry. I mean, in terms of number of iterations, but in terms of timing, as you can see, it's actually much faster. Yeah.
Okay, thank you. So another question I have is this idea of separating boundary conditions. Physically, I guess it means that the liquid should leave the boundary and the air should replace it. If you are simulating the full multi-phase, so if you actually simulate the air, do you need these separating boundary conditions? Or is this only a consequence of our typical approximation of saying the air is sort of a vacuum with a zero pressure Dirichlet condition on the surface? So just to summarize, if you did multi-phase simulation with the air simulation, do you think this would have, do you think that the separating boundary conditions are needed?
Yeah, with a multi-phase, yeah, we still need the separating boundary condition, but here we only deal with the air, with the fluid and the solid. So there are other cases like, for example, Betty students, he's working on it, like some bubble bouncing thing, which involves multi-phase. But it can be a future research.
Okay, great. Okay, thank you very much. We'll move on to the next talk.
Okay.
So, thank you very much. The final talk in this session will be accelerating distributed graphical fluid simulations with micropartitioning. The speaker will be Hong Chu.
In this talk, we will talk about running graphical fluid simulation in the computing cloud. We will propose a scheduling and load balancing algorithm called micropartitioning to speed up execution for this specific use case. This work is from Stanford University by Han, Omid, Chimayi, and Phil. Fluid simulation is important for graphics and movie industry. However, running fluid simulation is slow. The simulation needs to solve a Naive-Stokes equation with an iterative algorithm that requires tens of floating point commutations. Meanwhile, we often run the same simulation multiple times to find the optimal setting, which has the desired visual effect. Being able to iterate fast is of great value. On the other hand, the computing cloud is a promising solution. It is charged based on host hours, so using more hosts for parallel execution costs the same as running all computation on one host. The problem is, it is hard to achieve good performance for parallel fluid simulation. One key challenge for performance is the partitioning strategy. Imagine we simulate a fluid in a rectangle region. The blue part is fluid, where most computation happens. The white part is air, with little computation needed. If we draw a vertical line to partition the region, all fluid goes to one single node, so all computation goes to that node. The other node is almost doing nothing. The overall execution speed is the same as using one node, because simulation progress is determined by the slowest node. We get no performance speed up by parallelization. We can tackle the spatial load variance by drawing horizontal lines to partition the region. In this case, the computation is evenly distributed to two nodes. The computation time will ideally be cut to half. However, load distribution changes dynamically in fluid simulation. Even if we can find the optimal partitioning for one simulation frame, it does not necessarily work for all frames. Depending on whether the fluid stays on the left or on the bottom, sometimes horizontal partitioning is better, sometimes vertical partitioning wins. To summarize, the spatial and temporal load variance makes it hard to find the optimal partitioning. If we don't partition well, parallelization won't speed up execution. The classical approach to deal with load variance is dynamic load balancing. It repeatedly adjusts the simulation regions on nodes, so we can have different partitioning for different simulation frames, and we can deal with temporal load balancing. However, dynamic load balancing is not that simple in practice. It requires writing codes to move simulation state between nodes. It also needs a dynamic scheduler to coordinate the movement. Meanwhile, moving data introduces communication overhead, so the moving frequency must be carefully tuned for each application. Otherwise, the communication cost can be high. Dynamic load balancing also makes debugging harder because it is hard to predict which computation runs on which node. Because of these problems, we propose a scheduling and load balancing algorithm based on micro-partitioning. It performs close to dynamic load balancing algorithms, but without their complexity. It balances load by splitting the simulation region into many small partitions and randomly assigning them to nodes. It minimizes communication overhead by leveraging the performance characteristics of cloud computing network. We evaluate the performance on 4 applications using different simulation methods. We show it gives 2 to 3x speed up over a naive partitioning strategy. It is reasonably fast compared to state-of-the-art dynamic load balancing algorithms. There is a rich body of research work on load balancing. Graph partitioning algorithms are specialized for graph computations, and they usually assume no temporal load variance. Work stealing, as the simplest version of dynamic load balancing, is prone to repeatedly rebalance load, causing communication overhead. Distributed load balancing algorithm research focuses on scaling the load balancing algorithm on hundreds to thousands of nodes for scientific computations, while our work focuses on deriving a load balancing algorithm for running graphical fluid simulation in the computing cloud. We believe this is what is different. There are many simulation frameworks that allow implementing load balancing algorithms on top. They focus on system functionalities and programming abstractions. Our proposed schedule algorithm could be implemented on top of these frameworks. Micropartitioning has 3 key points. First, split the simulation region into many partitions. The number of partitions is critical in the scheduling algorithm because more partitions means more scheduling flexibility. Second, randomly assigning partitions to nodes. Because of randomness, all computation-heavy partitions won't go to the same node, so load can be balanced. Third, every node computes the assigned partitions in FIFO manner. The runtime may overlap communication and the computation of different partitions, so nodes spend less time being blocked by communication. This micro-partitioning scheme turns out to work well for graphical fluid simulation, but I suppose you might want to know why. First, can random assignment really balance load well in graphical fluid simulation? Does this always work, or are there any constraints? Second, if partitions are randomly assigned, more communication will happen between partitions. How do we handle the communication overhead? Is this going to be a problem? Next, we will try to answer these two questions. How well micro-partitioning balances load depends on the number of partitions. If you have 100 partitions per node, then on average, each node will get 60 busy partitions and 40 idle ones. But there will be some variance. Some nodes will get 65 busy and 35 idle. The important performance metric is the expected maximum load assigned to one node. So we define the load imbalance factor as the maximum load of all nodes divided by the average load, minus 1. As more partitions are used, the distribution of the load imbalance factor moves closer to 0. Intuitively, as we have more partitions, we are making more random choices. It is more unlikely for one node to always make the bad choices. Ideally, as we keep increasing the number of partitions, the load imbalance factor will keep getting closer to 0. So we get better and better load balance. We built a mathematical model to analyze the load imbalance factor. In this model, we do not consider the communication overhead. We assume the total amount of computation work is independent of the number of partitions. There are two conclusions from the model. First, the load imbalance factor is negatively related to the number of partitions per node. If we keep using the same number of partitions and increase the number of partitions, load will be as balanced as we want. Second, the load imbalance factor is positively related to the number of partitions. The number of nodes. If more nodes are used, we need more partitions to balance load to the same level. The relation here is logarithm, so we don't have a problem with tens to hundreds of nodes. In the prior analysis, we did not consider the drawback of having more partitions. One issue here is communication overhead. Because partitions are randomly distributed, more data are transferred between nodes. This is a valid performance concern, but in practice, this communication overhead does not matter that much in cloud network. Cloud network is designed for cloud applications like MapReduce. They exchange a large amount of data between every pair of nodes. Because of this, most cloud network offers high full bisection bandwidth, and it cares less about networking latency. This means the actual communication overhead of micro-partitioning has minimal performance impact. Let's look at the communication performance of cloud network in more details. This figure shows the transfer time between Amazon C4 machines. Transferring 25 times more data in certain cases only needs 3 times more time. Each data transfer has an initial latency, but sending more data adds more time very slowly. Here, the initial latency is caused by OS scheduling and virtual machine networking stack. This behavior means sending more data does hurt performance, but not that much. If other benefits brought by sending more data outweighs the disadvantage, the overall performance will be good. Moreover, communication can overlap with computation. Having more partitions increases the chance of such overlapping. When a node has many partitions to process, it's more likely that one partition can occupy a core, while another is waiting for data. So the core always keeps busy. In contrast, if every core processes only one partition, when that partition is waiting for data, the core has nothing else to do. As a result, the added communication traffic of micropartitioning is further mitigated. To summarize, we analyzed that enough randomly assigned partitions can give reasonable load balance. We also showed that the increased networking traffic is less a concern in cloud network. Altogether, this simple micropartitioning scheme gives good performance for running graphical fluid simulation in the cloud. We want to discuss the limitation of this proposed approach. It works well for most typical fluid simulation workloads. However, if the load is highly skewed and gathered in a small region, we need enough partitions to split the small region. In practice, the number of partitions does have a constraint, especially under uniform grids. In this case, sparse data structures are needed to partition such small region much denser, and at the same time keeping the number of total partitions small. In our evaluation, we examined three aspects of the scheduling algorithm. First, how much micropartitioning and randomized assignment help performance. Second, how is the performance of the algorithm related to the number of partitions? Third, how well this algorithm performs compared to other load balancing algorithms. We ran on 32 Amazon nodes with 576 cores in total. We used 4 applications with different simulation methods to demonstrate the algorithm can be generalized. We compare 3 cases of running the same application. First, use MPI implementations as the baseline. Second, use micropartitioning without random assignment. Last, add random assignment on top of micropartitioning. We see both micropartitioning and random assignment are helping overall performance. Altogether, they give 2 to 3x speed up. Note that we split the simulation time into 2 parts. The green part is the average computation time per node. The red part is the average time each node spent waiting for the other nodes. It is the time caused by load imbalance and communication. In all 3 cases, the green part is similar. Having more partitions increases the green part slightly because more computations are needed, merging data between partitions. Most improvement of the proposed scheduling algorithm is caused by reducing the red part. That is, improve load balancing and reduce communication time. We also run the same application and try changing the number of partitions used. Having more partitions initially improves performance, but eventually hurts performance. Because in practice, having too many partitions does introduce more computation and communication overhead. Also note that the optimal number of partitions depends on the application. Less than application, for example, has more skewed load, so more partitions are needed. The paper has more discussion about how to choose the number of partitions. We also evaluate our scheduling algorithms against other load balancing algorithms. We use flip simulation here. Geometric is a static load balancing algorithm that evenly partitions simulation regions to nodes. Reactive is a dynamic load balancing algorithm that uses the ongoing simulation frame to estimate load distribution for the next few frames. It uses the estimation to compute the optimal scheduling policy. The estimation could be wrong, and this hurts performance. Speculative tries to speculate load distribution in future, so it improves load balance quality. Birdshot's performance is similar to reactive, slightly worse than speculative, but it has a significant improvement over geometric. In conclusion, Birdshot is close to state-of-the-art dynamic load balancing algorithm, but it is much simpler. We compared the behavior of our scheduling algorithm with reactive. We found reactive needs to rebalance load at a fixed time interval. Otherwise, the load scale will increase and slow down execution. In contrast, random assignment combined with more partitions will have more even performance on different frames. Though dynamic load balancing algorithms like reactive can achieve better performance for one iteration, but as load changes over time, it might perform worse. This illustrates why dynamic load balancing algorithm is hard to perform well in practice without careful tuning. To conclude, our evaluation shows that micropartitioning combined with random assignment are effective performance techniques. It makes the computing cloud a more appealing platform for graphical fluid simulation. The solution leverages the performance characteristics of the computing cloud and at the same time builds upon existing load balancing strategies in scientific computation. That concludes my talks. Thank you.
All right, thank you very much for the talk. We have a little bit of time for questions, so please ask some questions in the YouTube comments if you have something on your mind. In the meantime, I will ask you one thing is that you talked about the impact that micropartitioning has on communication overhead in between processors, and you made a really good argument about when this matters and when it doesn't. Can you talk a bit about the impact of memory coherence when you do this? So, for example, randomly assigning processes, I'm sure it doesn't pay any attention to memory coherence, while a strategy that does maybe could gain some sort of advantage so that it doesn't, repeatedly send as much communication. Have you thought about this? Can you tell me a bit more?
Yeah, that's definitely a concern. Like when we have multiple partitions scheduled to different cores, the cache locality will be worse. So it could have a performance issue. But we saw like in our application when we have like long enough commutation slots, if the context switch only happens in a controlled pace, and then the cache locality performance loss is not that huge. So in practice, we saw like the perf loss is acceptable. Yeah.
Great, thank you. And this relates to the next question I have as well. I imagine there are extremes, right? Where if you do the micropartitioning too finely, like you mentioned in your talk, at some point you start paying for it in terms of communication. And maybe this is related to, there's a similar argument you can make about memory coherence. And you mentioned in the talk that you have plenty more to say about this in the paper. Since we have time, do you mind telling us a bit more about what factors this depends on, and how to choose the optimal number of micropartitions for a simulation?
Yeah, that is a very good question. And indeed, we saw like when we increase the number of partitions in practice, there are perf overheads. But as our understanding, the overhead mainly comes from having more partitions. There are more stencils being communicated between partitions, and there are more data being communicated, and there are more like data being serialized and deserialized. So in practice, we found it's not very easy to determine the number of partitions. There are two ways. So either we can do it empirically, maybe run a like very short simulation to see which one performs slightly better. And another thing is we have a kind of a mathematical model. So if you have a basic factor of the basic understanding of how load imbalance it is and how many partitions, how many cores you're using, we can give you an estimate. And starting from there, we can estimate the number of partitions. But this is very key parameter in the algorithm. That's true. Yeah.
Okay, great. Thank you very much. So this concludes the session. Thank you, everybody, for virtually attending and asking questions. And I hope you had a good time. Have a good break and see you next time.